Hey everybody, it's Ripley. I am back again. We're going to talk about hypothesis testing with two samples now. Now, think about what we did in the last chapter. What we had is we had a population, okay? And what we did is we guessed something about that population. So we had a null and an alternative hypothesis, and we either guessed something about the mean or about the population proportion, right? And we said that the mean equaled something, or that the mean didn't equal something, or that it was less than or equal to something, or something of that nature, okay? And then what we did is we pulled a sample out of that. So we pulled a sample out of that and we found an X bar, and we either knew the standard deviation of the population or we had to use the standard deviation of the sample. Remember, that was the difference between being able to use a z-test and being forced to use an s-test. If we were testing around p, remember, they had to be independent. It was more of a binomial situation. The requirements were in p and NQ were both greater than or equal to 5, et cetera, right? And then we did our test. We had a test of some sort, and then we either used confidence intervals, we used critical values, and we used p-values to determine whether or not, remember, wait, I've got a little ahead of myself. Remember, we always established an alpha. We also had an N, right? There was always an N here. And then we used all sorts of techniques to figure out whether or not it was feasible to reject the null hypothesis. Okay? Now, when we're testing two samples, what we're saying is, let me give you an example, okay? The easiest way to explain this is, I believe that the proportion of women that support a specific candidate is greater than the proportion of men that support a different candidate. Okay, so here's the way this works. Let me show you. We've got women over here. We have a population of women, and we have the population of men. Like before, like with confidence intervals and hypothesis testing, we're going to start with proportions. Okay, now we've got all women, all voting women, and all voting men, and then we do exactly the same thing. We grab a sample of them and we bring that sample out. We grab a sample of men and we bring that sample out, okay? And then we're going to figure out a p-hat for these guys, which we're going to call p-hat 1, and we're going to figure out a p-hat 2 for these guys, and we're going to have n's and p-hats and all sorts of stuff that we're going to deal with. And then we compare these two, and we decide whether or not there is truly a difference. Now, think about what, let me cut this off a little bit. Think about what the null and the alternative hypothesis for this would look like. Because really, if you think about it, if I know what the null and the alternative hypothesis look like, and I've chosen my alpha value, then all that I need is a test value. All right? And I'm not going to insult your intelligence by going through a whole bunch of these. What I'm going to do is I'm going to give you the test value. I'm going to give you an example straight out of the book, because by now, in other words, I'm going to give you what the test is. In other words, you know, whether it's a Z, a T, whatever. I'm going to give you, I'll write up what the assumptions are. And then I'm going to give you guys an opportunity to try it on your own, and then I'll do it out for you, okay? So think about this. The null and the alternative hypothesis, just like before, the null hypothesis is, that the proportion of women is equal to the proportion of men. It always contains the equality, always, okay? And then this can either be P1 is not equal to P2, P1 is greater than P2, P1 is less than P2, etc. Just like we did before, okay? Now, there's a difference with this. We don't traditionally do this with proportions, but I do want to set up. Let me say, I believe, I'm going to make a claim. I believe, that the difference in support of, wow, that's terrible handwriting. I'm sorry, you guys. The support of candidate A of women You guys, the construction's going crazy today, so bear with any weird noises, okay? Candidate, what's going on here? A of women over men is 5%. In other words, it's 5% higher in women than it is in men. I suppose I could have written that a little bit better. Now, the difference between when we're doing this with just one sample versus two samples, you have to realize that what we're doing here is we're talking about two samples. The difference between when we're talking about one sample and two samples is that we can actually talk about differences. So I could actually write the null hypothesis up for this as P1 minus P2, the true proportion of women. 5% is gonna, let's make that 8%, because otherwise we might get a little confused with alpha. Let's say that it's 8%. Okay, that P1 minus P2 equals 0.08. All right, versus the alternative hypothesis, which is P1 minus P2 is not equal to 0.08, is greater than 0.08, is less than 0.08, etc., etc., etc. Now this is pretty cool because it allows us to do this little funky business right here, which is really nice. In other words, we don't just have to say that they are equal to each other. Because really, if you think about it, let me change colored pens right here. This is exactly the same as saying P1 minus P2 equals 0. We can be much more specific in what we believe the difference to be, and then we can test that difference. All right? Now remember, this only works when we're talking about two samples. Not just one sample, because then we pull a sample out and we say, okay, the mean or the proportion or something equals a value. But now we're talking about the differences between those two samples. All right? Okay, cool. Now, before we get crazy, like I said, these are really simple. We're going to blow through these quickly. The only difference, excuse me, between what we're going to do here and what we did in Chapter 8 is the test, the T, the Z, etc., is a little more complicated, but we're not going to panic, all right? The first thing that we need to do is we need to talk about the assumptions, okay? First things first, the assumptions. So right now we're talking about differences. That looks terrible. Whoa, wow, differences, pardon me, excuse me, in proportion. Let's do this one first, just like we did before. Start with proportion, work our way to means, okay? Assumptions. All right, number one. The number one assumption is that the samples are independent. Samples are independent from each other. Now think about that. What that means is the probability of a certain person favoring a candidate, a woman favoring a candidate is different, is unaffected by the probability that the man favors a certain candidate. Now, think about that in the context of the problem that I just talked about. In other words, you couldn't sample a husband and a wife. Theoretically, there'd have to be a strong argument that said, okay, he does not affect my voting and she does not affect my voting, because those wouldn't be independent, would they? I mean, think about that. If you affect one another's voting, it's like, honey, I think you should vote for candidate C, not candidate A. Well, guess what? You potentially violate this independence assumption, okay? And then standard issue, it's a proportion. So from each population, in my case it was the men and the women, all right, from each population, we draw a sample, all right, we'll call it of size n, such that NP1 and NP2 are both greater than or equal to 5. Just like before. All right? Just like before. Nothing to it. Okay, now, the formulas for this are beefy. You're going to have to bear with me for just a second. Okay? Now, again, just kind of plant it in your brain, just to keep it simple. Think of P1 as it's the population proportion for population 1. Population 1. In this case, the women. Okay, P2 equals population proportion for population 2. In other words, those are the parameters. Okay, those are the parameters. Let's see. N1 is sample size, and this is going to get a little boring. Sample size from population 1. Okay, and N2 is the sample size from population 2, et cetera, right? X1 equals the number, remember, this basically comes from binomial, all right, of hits, just like before, from from N. Whoa, sorry about that, my eraser's acting goofy. From N1. In other words, I take a sample size of, of 600. I say, do you favor candidate A? X1 would be the number of women that said, yes, I favor candidate A. Okay, so let's see, X2 equals number of hits from N2. Easy peasy. So I know that P1 hat equals sample proportion for pop 1, and P2 hat equals sample proportion for P2, or for population 2 portion. Sorry, you guys, that's terrible. I apologize. Okay, so nothing to it. I also know that, let's see, might as well be exhaustive here. I know that 1 minus P1 hat is equal to Q1 hat, and 1 minus P2 hat equals Q2 hat, etc. Now, there's something in here called a pool. We're going to need this. This is called a pooled sample. I'm going to change colors. You know what? Just because this is new and different, and I don't want to be glib about announcing this because we're going to use it in our formula. We're going to use it in our test statistic. Okay. All right. Here we go. So we're going to do. Let's do red. We're going to do pooled sample proportion. Now, again, why we use this, why this is what it is it's above the scope, it's beyond the scope of this class. This is an introduction to statistics. I want you to see it. We're going to do a lot of these by hand. These get a little trickier to do in absence of, to do some real compelling work in absence of computers, but computer software does all of this for you, and it actually spits out, it's got this output that it spits out. But I want you to do these by hand because I want you to see why. And we're not going to do many of them. I mean, we're really only spending a day in this chapter, so it shouldn't be too much torture for you. Think of this as, this is all that we're doing is we're pooling x1 plus x2, and we're dividing it by n1 plus n2. And I'll show you why we need this in just a second. So we know that Q, the pooled sample Q really is just equal to 1 minus this P bar, okay? Think of it almost, I mean, if you look at it, what it is it's the mean of the proportions, right? It's the mean, it's the overall mean proportion. So you take the sum total of all of the, yes, I support candidate A, and I divide it by the total number. In other words, this thing ignores any differences between the populations, okay? Now, here's where it gets fun. All that you need is a z statistic, okay? We're going to do it with z, remember, because we know with binomials, as long as this guy right here is satisfied, we're in good shape, all right? Let's see. So all that z is it's P1 hat minus P2 hat, okay, minus P1 minus P2. Now remember, samples, parameters, and I'll make you guys use these here in just a sec, so no panicking, okay? And this is divided by the square root of P bar Q bar over N1 plus P bar Q bar over N2, okay? That's all that it is. That's the z, okay? This is if we're going to use, this is the guy that we're going to use if we want to do a p-value or a critical value, right? And then for a CI, you can almost look at it and figure out exactly what it is, all right? You can almost look at it so check it out. I know that the difference in P1 minus P2. Remember the difference in the proportions, excuse me. All that it's going to be is P1 hat minus P2 hat minus the error. Put a little thingy-dingy there. And we're going to have P1 hat minus P2 hat plus the error. Now, what's the error? We could actually go through our algebra here, but I'm not going to force you to do that because you would all revolt on me and I'd end up dead, and I don't want that. And this is just z alpha halves, just like we did before, right? So it's based on our alpha, and then I'm going to have square root of, this is going to be P hat 1 Q hat 1 over N1 plus P hat 2 Q hat 2 over N2. Okay? That's if I want to build a confidence interval. That's it. There's no difference. In other words, let's be careful. There are differences just insofar as where this test statistic comes from. It's more complicated. It's a more complicated numerical process. However, if you think about it, it's still going to work out the same way. Once I get this number, I'm either going to look at the p-value, I'm going to look at the critical value. I could build a confidence interval and figure out if my mean ends up, my proportion ends up in this confidence interval. In other words, the techniques that we use to determine whether or not to reject or accept the null hypothesis, we're still just testing around this guy and this guy. These are just the values that we use, all right? So there are your test statistics. These are what you're going to use. Are you going to have to memorize these? Of course not. In fact, we're going to hang them up with the assumptions in the room so that you'll be able to use them. However, you are going to have to be comfortable using them. So let's go through a process. All right, let me dig a problem out for you guys directly from your textbook, and I'll let you do it and I'll do it, and we'll compare notes afterwards and we'll see how we did. Okay? Okay, let's put it to the test. You ready? On page 458, there is a problem called Are Seatbelts Effective? It's number, what number is it? It's number 16. Okay, are seatbelts effective? Is it A or E? It's an E, isn't it? I always screw that up. Effective. Okay, now here's what I'd like you to do. I'm going to push, I'm going to stop, and then I'm going to do the whole problem out down here. But I would like you to try it all on your own. All right, it's number 16. It's not number 15. Number 15 is just building a simple confidence interval. Okay, now I'm going to do it all out, and then I want you to check your work. If you can do this one, you're golden. Okay, when I come back, the problem's going to be completely done here. And I'll walk you through it. It won't take very long at all. Okay, so good luck. Hit pause. Try it out on a piece of paper, and I'll meet you back here in just a sec. All right, here we go. Hopefully you ended up with something like this. Are seatbelts more effective in saving lives? All right, they either, well, I think in the problem it says, I forget what it says. It says, is there a higher rate of fatalities in drivers that don't use seatbelts? Excuse me. So basically, are the population proportions between, let's try this again, for drivers using seatbelts, which would be these guys, versus drivers that aren't using seatbelts, is the proportion of fatalities higher in those not using seatbelts? Well, we know, I mean, this is a pretty obvious problem, but watch how it plays out. They're either equal, or we know that we're really checking to see if those using or not using seatbelts is higher than those using seatbelts. So all I did is I stumbled through, what I really needed was P1 hat and P2 hat, right? So I just stumbled through. Let's see, X1 was 31 out of 28, 23. Clearly they're independent, right? So, I mean, you can't be wearing a seatbelt and not be wearing a seatbelt. I suppose you could gather it from the same accident, like some guy was wearing a seatbelt and some guy wasn't, but that doesn't really matter. All right, so this guy right here ends up being my sample proportion of people that died who weren't wearing seatbelts. This was a sample proportion of people that died who were wearing seatbelts, and then I found my pooled. I suppose I was a little remiss here. I didn't actually come up with Q bar, or my pooled 1 minus P, right, which would just be 0.99, what is that, 56? Okay, I built my little thing. I chose to use a critical value because I had a sneaking suspicion that it was going to be more difficult to find the p-value because I was guessing that our test score was going to be huge, and as it played out, it was. So all that this is p hat 1 minus p hat 2. We know because of the way in which our null hypothesis is written, I know that p1 minus p2, the true population proportions for both samples, or excuse me, for both populations is 0. I plugged, I chugged, and this is what I got. And then this is my summary. Since z equals 6.19 falls in the critical region, it's larger than 1.645. By the way, that was my critical value, right, for alpha equals 0.05. Excuse me, which, I mean, if you think about this, if we had to figure out the probability of getting values at least as extreme as z equals 6.19 standard deviations away from the mean, the probability of that's going to be very, very small. It's certainly going to be less than 0.05. We reject the null hypothesis. It appears that fatality rates are significantly higher in drivers not using seatbelts. Ta-da! And we're done. And that's it. That's how it works. That's all we got to do. It gets a little trickier when we build confidence intervals, but we'll do that in class. We'll play with that. It's still this, it's just a variation on the theme, okay? The theme of, are we going to use critical regions? Are we going to use p-values? Or are we going to use confidence intervals? All right, it's just the same. It's just that the calculation gets a little bit nastier. Okay? We're going to go ahead and move on to the next section, and I'll see you in class tomorrow. All right, everybody, welcome back. We're in the next section now. Remember, just like we did with confidence intervals, just like we did with hypothesis testing about one mean, we're going to do, we start with proportion, we move on to mean. So we're going to do means. We're not even going to mess around with variances. That's a whole nother deal. However, it's basically the same thing. All we're going to do is we're going to test a null hypothesis and an alternative hypothesis. And typically, but not always, typically you will have that the mean of one population is equal to the mean of another population. And then you're either going to have the mean of one population is not equal to the mean of another. The mean of one population is greater than the mean of another. Excuse me. Or the mean of one population is less than the mean of another. Remember, what we're doing is we got two populations. Now, these are called independent samples, which implies that these populations have to be independent. This population is going to have its own mean. This is going to have its own mean, which we don't know. We're going to draw out a sample, just like we did before. We're going to draw out a sample here, and we're going to compare them. We're going to get X bars, etc., etc. Okay? Fair enough? Nothing to it. Now, we're going to assume that the samples are unknown, or excuse me, that the standard deviations are unknown. Okay? And all we're going to do is, just like before, we're going to write up our assumptions, pardon me, and we're also going to write up our test value. All right? Then we'll jump right into independent samples where the standard deviations of both populations are known. And I'll give you that, and then we'll do a problem together. Okay? Sound good? Excuse me, I'm getting a sip of caffeine here. Starting to flag. Okay, so our assumptions. I'm not really starting to flag. I just want caffeine. Watch out. Yeah, you'll see my writing get a little crazy. Let's see. Number one, let's see. The assumptions, of course, are always SRS. So we want simple random samples from both populations. Both pops. Maybe I am having. Look at that. It's crazy. Pardon me. Of course, the samples are independent. Samples are independent. In other words, they have no effect on each other. Dependent. Now, this is a biggie, okay? Either, whoa, they're a little crazy. Now, it's either or both, of course. You can have both if you want. So either the first sample is greater than 30 and the second sample is greater than 30. In other words, the sample sizes are greater than 30. Or both samples are drawn from normal populations. Normal pops. If you don't have either one or the other of this, then you can't do this. You're screwed. You got to go digging for way more information. Okay, you need more data values. Okay, so that's what we got going here. Now, watch how this works. Excuse me. So simple to work with. What we're going to do is we're going to do a T. Remember, if we don't know sigmas, we always have to go with T. Now, we'll talk about degrees of freedom here in just a second. Okay? So all that we're going to do is we're going to take the mean from the first sample minus the mean from the second sample. From that, we're going to subtract the population mean, or what we suppose that it is, what we think that it is, from the first, and the population mean from the second. And remember, those always come from your null hypothesis. All right? Remember how before we talked about this? You may or you may not. There's nothing that says that I have to let the mu1 equal mu2. I could actually say that I could say something like mu1, I'm running out of space here. I'm going to erase these little alien eyeball thingy-dingies. I could actually say that mu1 minus mu2 is equal to 5. And what that says is that the difference between the population means is 5. For example, let's say that I test the miles per gallon in a Honda versus the miles per gallon in a Toyota. And I believe that the difference in miles per gallon in their top-of-the-line car is actually 5 miles to the gallon. All right, that would be an example of, instead of mean 1 equaling mean 2 and us testing that, I don't know if Honda's got a higher miles per gallon or if Toyota does, but let's say that I know that Honda does, and I'm trying to pin down what it is. Well, that would be an example where we say mu1 minus mu2 equals 5, rather than mu1 minus mu2 equals 0. Okay? Okay, so hopefully you see that, and again, you'll get to play with that some more down the road. And this is divided by the square root of, and I take the sample standard deviation from the first sample, and I square it, and I divide it by, excuse me, n1, and I add that to the sample standard deviation from the second sample, and I square it, and I divide it by n2. Sometimes you'll hear this referred to as the pooled standard deviation. All right, where again, it's kind of beyond the scope of the mathematics for this course. All right, I just want you to see how this thing works. All right, if we're going to do a confidence interval, CI, you can probably tell where this is going to go. You know that mu1 minus mu2 is going to live between two values, which is going to be x1 bar minus x2 bar minus the error, and then x1 bar minus x2 bar plus the error, and your error term is just equal to your t sub alpha halves, which we got lots of practice with dealing with that, and then this s1 squared over n1 plus s2 squared over n2. That's our error. It works just the same. Now, question is, what are degrees of freedom? We are going to keep it super simple. The degrees of freedom are just, all it's going to be is the smaller number. Wow, sorry about that. This caffeine is starting to kick in. Smaller of n1 minus 1 and n2 minus 1. That's it. That's all there is to it. Okay? So, not to panic, piece of cake. That's our test value. That's our confidence interval. We know how to find degrees of freedom. There's a more complicated way and a more accurate way really to find degrees of freedom, but we really don't care. Believe it or not, there's not a whole lot of difference between the two. Okay? So let's go ahead and I'll find a good problem for us to do. I'll throw that up there and I'll throw the solution. And guess what? Oh wait, you know what? I lied. Let's change the business here. What if sigma 1 and sigma 2 are known? All right? Now, hopefully you can figure this out. Remember, if I know what the parameter standard deviation is, right? If I know that, then I don't have to putz around in this T land. Remember, T is crazy. It's got a family of curves. They're not normal. It's not normal curves. They look normal, but they're not all normal curves. It's just this family of crazy curves that sort of expand for us to what would be the right word? To accommodate for accuracy and precision. All right? However, watch. If I know the standard deviations from both populations, and you may say, well, I don't know that that's terribly reasonable. Well, think about my Honda and Toyota deal. I mean, think about it. They made a lot of cars over the course. They can probably figure out what the standard deviation is, or they can create confidence intervals to do that for them. Okay. All right. So watch what happens. T turns into Z. If you know sigmas, T always turns into Z. All right, and we just end up with x1 bar minus x2 bar, let's see, minus mu1 minus mu2. That's often 0, which is nice. It makes life easy. And then instead of those S1 squares, I've got sigma 1 squared over N1 plus sigma 2 squared over N2. And the best part is when I'm dealing with Z, no DFs, right? Because I get to play ball on the standard normal curve. Okay? And if you come over here, then I know, I know that the error bound for this guy is just going to be exactly the same thing, only I'm going to have a Z alpha over 2 root sigma 1 squared over N1 plus sigma 2 squared over N2. All right? Now, if I'm moving too quickly, if these formulas are coming out too fast, just yell at me, pin me down in class, and we'll get it done, okay? So don't panic on that. All right? So I'm going to find a good problem for you, and we'll hop into it, okay? Okay, here's what I want you to try. I want you to go to page 472, all right? And I want you to try problem, let's go number 21. All right, now I want you to go through the entire problem and read it first and ask yourself, are the assumptions being met? Are we talking about independent samples? Do we know, what about our standard deviation? Since standard deviation seems to be the key here, we got to pay attention to what we have as far as, if I know the population, if I know the parameter, then I get to play on Z, and that's easy because that's just the normal curve. But if I don't, then I'm going to have to use that silly T-chart and play around with that one. So play around, enjoy, and I'll meet you back here after you've tried it out, okay, with the solution. All right, let's roll. Now, you probably got an answer that you're like, oh my God, I must have made an error on, but it's actually very compelling, and it's interesting to talk about what's going on. So first things first, I like to organize my thoughts with problems like this. I let mu1 equal my high interest FICO people, okay? So these are the people that are paying a high interest. My mu2 are my low interest FICO people, so these are the scores that came out of that. So my null hypothesis is that they're equal, that they're FICO scores. Think of these FICOs, I meant FICO scores. So these are the FICO scores of the people, so they're either equal or that the high interest people have lower FICO scores than the low interest people. Okay, alpha equals 0.01, and my degrees of freedom, remember, you take the smaller of the samples and you subtract 1 from them, and in this case we ended up with 39. All right, because they both have 40 in the sample. Then I just wrote down what I got. So my FICO scores, my low interest people, I took the average of their FICO scores, and I ended up, FICO is just it's a credit rating agency, okay? It's based on all kinds of things. We'll talk about it more in class. There were 40 of them. The average was 594.8 with a standard deviation of 12.2. Excuse me, in the low interest, the people who paid lower interest on their mortgage, there were 40 of them. They had an average of 785.6 and a standard deviation of 16.3. I chose to use the critical values. When I'm dealing with T's, why do I have to use T's? Well, that should be obvious. It's because I don't know the population standard deviation. Otherwise, this would be a lot easier because I just play ball on the standard normal curve. So my alpha is 0.01. Ooh, that's a little different. But all that I do is I'm going to draw my curve. I'm going to use critical values. I go to the chart, the T-chart in the back of the book, and I go to degrees of freedom, which is 39. I go to the area in one tail. It's clearly a left tail, remember. My inequality always points in the direction of the tail. And I got a critical value of negative 2.426. There should be a negative in there somewhere. Sorry, it's a little hard to see. What the... There, negative 2.426. Then all of a sudden, all hell breaks loose. But you may already be able to tell something's crazy here. I've got a mean of 594.8 and 785. That's huge. That's almost 200 points. And my standard deviations are very small relative to those, right? So there's no way that somebody who's scoring in this group, in this high interest group, I mean, if I get 3 standard deviations away, it's only 36 points, and I'm almost 200 points away from the low interest. So when you plug it in, that plays out numerically. You end up 60 standard deviations away from the mean for their difference. Now, what does that really say? Let's wrap our brains around that, because if all you do is follow the numbers, it's kind of like following the end of your nose. You won't really know what's going on. In other words, if these two were equal, the number of standard deviations away from the mean that we would be 60 standard deviations away. Think about what the p-value would be 60 standard deviations away. I mean, the p-value would be less than 0, right? They'd actually, well, there's no such thing, but clearly it'd be so close to 0 you wouldn't be able to tell the difference. All right, negative 59.27 ends up, well, not here, but off the screen, around the corner, and around the world with respect to this curve. So clearly we're going to reject the null hypothesis, which we pretty much knew before. There's huge evidence that people with lower FICO scores pay higher interest rates. Now, I can't do a confidence interval around this because I've got a not equal to here. Now, you may say, Ripley, in your lectures, in your online lectures, you're not doing a whole lot of confidence intervals. It's because we're going to do a bunch of them in class. By the time you're done, you'll have more than enough practice with confidence intervals. Okay, so this was a sort of an exaggerated problem to help sort of, I don't know, make some discussions about what happens when you get a hugely different number like this, or excuse me, you get a huge t-value like this. Well, it just cries that there's a huge difference between these two values, which makes sense, right? For those of you that don't know anything about mortgages, the first thing that they do is they check your credit rating. It's the first thing, and they're like, oh, okay, well, your credit rating's in the 700, so here's going to be your interest rate. And if it's lower, then the interest rate goes up. All right, hope that was helpful. We'll see you tomorrow. All right, now there's another more kind of esoteric issue that we have to deal with, and hopefully you're saying that when we're testing means, right? We got mean 1, we got mean 2, and I'm checking to see if they're unequal, if they're greater than, or if they're less than. That's really, this would be the alternative hypothesis, right? Because the null hypothesis always contains the equality. But the question is, what do we know about standard deviations? All right, so thus far we've played with ideas of, I have no idea what standard deviations are of these populations from whence we're drawing the samples, or I do know what the standard deviations are. And the difference between the test that we use is whether we use a z, excuse me, that would be a t, whether we use a t or if we use a z, right? Now there's one more special case, and this one's kind of weird. So let's say that I don't know what the population standard deviation is of either sample, but I can assume that they're equal. So let's say, for example, I lay down some new turf on a really big I don't know, playing field, sports field, whatever, right? And I want to know the rate of grass growth, but I used, like it's just a different, like, I don't know, it's just a really huge field. So I'm basically using the same treatment on these things. I have no idea what the standard deviation is of the population, but I can assume that it's equal, right? In other words, the manufacturer didn't publish the standard deviation of the rate of grass growth. So anyway, hopefully you're understanding. So don't know what it is, but I can assume that it's equal. Now, there are some assumptions with this type of test that we're about to do. First and foremost, as always, we want the two samples to be independent. We want, which in the case of the grass, right? So you get this big old, whoa, you get this big old athletic field, and I'm testing a patch over here and a patch over here. They're clearly independent. They're not growing into one another. They both come from a simple random sample. Let's assume that we cut this field up into a bunch of pieces and we flipped some coins and we figured out which patches we were going to test. And then now this is a biggie, and this one's kind of confusing. Now either or both of the following assumptions have to be met. Either both N1 is greater than 30 and N2, in other words, our sample sizes are both greater than 30. Or we can assume that the samples from a normally distributed normal population. Okay, in other words, the population has a normal distribution,
In which case, we can get away with smaller n sizes, which we've discussed ad nauseum. Okay, now, again, I'm not going to do any, I won't bore you guys with a bunch of examples with this because it's basically variations on a theme. Now, know this, when you start messing around with software, and you're going to have little modules that you work through in your textbook dealing with different types of software and with your calculator, it's going to ask you these kinds of questions, right? It's going to ask you if the standard deviations are known, if the standard deviations are equal, but are unknown but equal, or unknown period. And then it will use a different test, and you're about to see why here in just a second. All right, the t-test that we use is this. It's basically the same thing as we used before. It's simply x1 bar minus x2 bar minus mu1 minus mu2 all over. Now here's where all hell kind of breaks loose. What we're going to have is we're going to have that exact same thing. Remember where we had the S1 and we squared that? Now I'm not going to put the S1 in there because I'm going to put something else in there. Over N1 plus, that's supposed to be an S. Oh, that's squared. Sorry. This is squared over N2. Now instead of our sample standard deviations, what we're going to use is called a pooled standard deviation. And this is where technology is really, really helpful because the pooled standard deviation is this. You ready? It's awful. So the pooled standard deviation is, it's going to be N1 minus 1. So sample size from the first sample minus 1 times the standard deviation of said sample squared plus N2 minus 1 times the standard deviation of that guy squared all over N1 minus 1, I don't know what that noise was that I just made, and N2 minus 1. All right, now, I will tell you that when I teach this class, you never have to calculate this guy. I always let students use technology to be able to figure this thing out, okay? But you may end up with an instructor that makes you do that by hand. Hopefully they'll just make you do it once. Now the other question that we have, since we're using a t-test, we potentially could be using a t-chart, is what are the degrees of freedom? And the degrees of freedom for this guy, and this is all of those assumptions that you've got to keep straight. That's the hard part. It's like, whoa, what am I doing and when am I doing it? Because it changes. Remember before, we took the smaller of the two when we didn't know what standard deviation was. Well, in this case, we sum the two and we subtract 2 from it. So it's like we take this cumulative degrees of freedom as opposed to what we did before. All right, now, last but not least, and then I will shut up, is let's talk about if we are building confidence intervals. So I know the difference between the two. I'm going to build this guy right here is just x1 minus x2, these bars, of course, and this is just going to be minus e, and this is going to be less than x1 bar minus x2, and then plus e, and then e is predictably, you ready? All I do is take e is equal to that t alpha over 2, right? That just builds out our confidence interval, and then I multiply it by this guy right here, which is just the pooled standard deviation squared over n1 plus the pooled standard deviation squared over n2. And that's it. And again, the degrees of freedom for this guy are just this. Okay? Okay, so what you have here when you're comparing means is if you're comparing independent means, right, where we can assume that the samples are independent, they come from independent populations, excuse me, is 3 different possibilities of skills that you have to use, right? So again, let's go over them real quick. If I know sigma 1, sigma 2, if this is known, then I'm off to the races. I use Z. If sigma 1, God, my handwriting is really bad today. Too much caffeine is not known, then I use T. But I use T where I don't have to worry about this pooled sample standard deviation, right? I don't have to use this. I simply use the standard deviations of each one of the samples. And I square those and divide by n1, square the other one, divide by n1. And then I have sigma 1 equals sigma 2, which is what we just did. Now notice, everything changes, right? Because if I'm using T, I have to respect degrees of freedom. If I'm using Z, I don't have to. I'm all good. And everything has to do with that standard deviation. Everything has to do with standard deviation. It's the ball game. It really is. All right, I will shut up. Thank you for your time and attention. I hope you enjoyed this section. Have a good day. Bye-bye.